Welcome back to the classroom. My name is Mr. Wong. Today we're going to be covering Module 8, From the Universe to the Atom. I'm going to be looking at inquiry question 5. So we're into the very end part of HSC physics. I'm going to be analysing the evidence that suggests that protons and neutrons aren't fundamental particles, and then also the existence of subatomic particles other than protons, neutrons, and electrons. Now, before I start, I just want to quickly refer to what we mean by subatomic. Okay, subatomic, if we break down the actual language of it, so we go sub, so smaller than, and then we have atomic, which means the atom. So we're trying to find things that are smaller than the atom. Now, that's pretty obvious. We already know three. We know that the electron, we know that the proton, and we know that the neutron are all found inside the atoms. And so they are what we call subatomic particles. But we're going to show today how the electron is actually the only one out of the three that can't be broken down, or at least not to what we know right now. But we know that the protons and neutrons can be broken into smaller components. So there are smaller parts with these that can be found. Let's have a look. Okay, so we're going to identify some evidence that shows protons and neutrons are not elementary particles. And then at the end of this, hopefully you also know some examples of other types of elementary particles and how they were discovered. Now, for your textbook reference, those are the pages you're looking for. Just before we start, let's just really recap on everything we've done in Module 8, where we talked about finding the smallest type of matter, or type of mass. We started with 400 BC with a guy named Democritus. We didn't talk about him, but John Dalton was the actual first person that proved the existence of the atom. Democritus only theorized that something like that existed. We went to then J.J. Thomson, who identified there are things smaller than the atom, in this case electrons. And we found that Rutherford and James Chadwick also found other components inside the atom, specifically the proton and the neutron. I want to show you this chart here. We aren't talking about it specifically today, but it will come back later on. It's called the Standard Model of Matter. And this standard model basically shows you all the fundamental or elementary particles that exist in the universe as of what we know right now, or from some of them what we predict that exist. So all these different particles, we have your quarks here, and we have your leptons here, and they can form larger components. So quarks can combine together to form protons and neutrons. Your leptons, like your electron, can exist on their own as well. You have here the gauge bosons. Okay, these are what would you describe as particles that help integrate and mediate interactions between these elementary particles. So we have the photon, that's known to allow for the works of electric fields and magnetic fields. We have the gluon, so to glue the nucleus together, so the strong nuclear force. The Higgs boson is a very famous one, and also a very recent one that was discovered in 2013. And it's the idea that this is the particle that ensures the transfer from energy to mass, how that occurs. Higgs boson is seen as the God particle, or the particle that dictates how matter actually develops its mass. Okay, so that's the model, as you can see, there are no protons, there are no neutrons in this chart here, so they aren't part of the elementary particles. So this is what we're going to look at first. How do we prove that protons and neutrons aren't elementary? Okay, this might need to go back a little bit with Module 6 stuff as well. We know that an electron is negatively charged, and charged particles interact with magnetic fields. Okay, this implies that given the electron does bend when exposed to a magnetic field, the electron itself must have a magnetic field that's unique to it. So what we can predict is if it's a charged particle, they will have an intrinsic magnetic field inside of them. Okay, so only magnetic fields can interact with other magnetic fields. Just because it's a particle doesn't mean it doesn't have its own magnetic properties. Okay, so electrons has its own magnetic field, has magnetic properties. Keep that in mind. Because what we actually know is neutrons actually have its own intrinsic magnetic fields as well. Now we know that neutrons don't have a charge, but it does have an intrinsic magnetic field. Okay, so what that could indicate is within the structure of the neutron, there might be some internal structure where there might be some slight charge distribution. So in total, it adds up to 0, but there are distributions of charges where it could be a bit positive and a bit negative. And we actually know that to be true today because a neutron is actually made up of 3 quark types, or 3 combinations of quarks added together. We have the up quark, maybe I'll write that down. So we have, it's made up of 1 up quark and 2 down quarks. Okay, so that's what they are made of. Okay, that's the particle-antiparticle pair. We also know that a neutron, a free neutron, is unstable. It tends to undergo beta decay. This is an important fact that we'll talk about in a second here. But first point we need to understand, the fact that it has an intrinsic magnetic field would imply that it has some charge properties to it. Now if the neutron is neutral, that means those charges must have cancelled each other out at some point. So that's an important thing to consider. And then obviously, why do we think the proton is not an elementary particle? Well, firstly, it has a very similar mass to a neutron. So both of these are a lot more massive than an electron. And so given the fact that the neutron was seen to have an internal structure, then perhaps a proton with a similar mass should also have a similar internal, or have some form of internal structure. And we actually know that to be true. So for a proton, it's actually made up of 2 up quarks and 1 down quark. You can see it's just a difference in the type of up and downs. That's the thing that differentiates the difference between the proton and neutron. Okay, so the way we can actually demonstrate protons aren't fundamental particles is actually through beta decay or beta emission. So going back from inquiry 4, when we first talked about the different types of radioactive decay, we talked about beta decay. So in this case here, when beta decay occurs, the neutron is converted into a proton, or changes into a proton, and an electron is emitted. So the proton number is increased, the neutron number is decreased by 1, so neutron is converted into a proton. In a positron emission, okay, so a positron is essentially, I'll just get my pen, positron should be positive anyways, the proton is converted into a neutron and releases a positron. So what you can see here is sort of the reverse of each other. So we can show that the protons and neutrons can convert in between each other, vice versa. So if I can make a proton, or if I can make a neutron into a proton, and I can make a proton into a neutron, then they can't be fundamental particles, because the idea of fundamental particles is they can't be broken into smaller things. They cannot be broken into smaller components. Or, to be honest, they shouldn't have any additional components at all. The fact that protons and neutrons can have positron decay or positron emission or beta decay and convert into each other, that would imply that they can't be fundamental particles or elementary particles there. Okay, so the next one we're going to be talking about is the neutron and proton. So as we talked about here, now the neutrons are not fundamental particles because neutrons have an intrinsic magnetic field. This indicates that the neutron has some internal structure and contains charges that add to zero. So there's a slight charge distribution. Okay. A free neutron is unstable, undergoes beta decay, so it doesn't naturally. So that lack of stability would also show that it's not a fundamental particle, because you would assume if it's a fundamental particle, it should be relatively stable. Evidence that demonstrates protons are not fundamental particles. We can see that in beta decay and positron emission. So positrons and neutrons can convert into each other. Neither can be an elementary particle, as they can be formed by one another. So it demonstrates components where one can go into another. So that's another example which demonstrates that positrons or protons and neutrons aren't fundamental. The fact that they can be broken or formed by something else. So there's that. So yeah, so the fact they can be formed by other particles. Okay. Alright, so the next thing we're going to look at is evidence that suggests the existence of other subatomic particles. Now today we're just going to go through one example. In our next lesson we'll go through maybe one or two more, and hopefully that gives you a better kind of branch of understanding of where we realize all these different particles come from. Okay, the first way we can actually detect fundamental particles is obviously just looking at natural radio decay. So electrons, which are beta rays, were first discovered through the analysis of photographic plates. So it creates these kind of smudges, and this is actually a detection of radiation. And this is a great way of actually analyzing radioactive rays, cosmic rays, and all those kind of things, because we know that radiation is a very, as we talked about before, photons is also part of the standard model of matter. Now, one of the uses that we can actually use to find radiation is also called the Wilson cloud chamber. So the structure is very straightforward. You have dry ice surrounding this sort of glass block. Inside of it you have vaporized alcohol, and what actually happens is when you put a radiation source through it, the let's say alpha beta particles, because they're really high ionizing ability, so they interact with the gas particles of the alcohol, and they produce these lovely cloud trails here. Now, as you can see, some are really straight, some are sort of more stocky, blocky, and curved. Now, what we actually know is the sort of fatter or wider strips represent a alpha particle, and then sort of the thinner dot lines are more sort of beta particles there. So we can actually use that to detect radiation, which leads us on to an interesting thing that you can do with it, and that is to expose it to a magnetic field. Now, the person who actually looked into this is Anderson, Carl Anderson, and he did some work with, or he was known as the first person to discover a positron. So this is actually one of the photos that was taken to demonstrate the motion of a positron. Okay, so we know that a positron is just an antiparticle to an electron. Okay, now the way he worked it out was when he had his cloud chamber, he exposed it to a magnetic field, and he saw that the electron made sort of this circular motion like so. Okay, so that was known. We already know that was the beta particle. That's negative. What he also found was this second rotation, and that was a positron, which is basically a positive component of the electron. Now the shape of the lines, as we talked about in terms of the thickness was about the same. So you can expect that the mass was the same, you were dealing with something quite similar. However, it curled in the opposite direction of what the negative charge was expected to do. So this demonstrates that the particle that he was looking at had a positive nature to it, and so he deduced that this was a antiparticle pair of our particle, which is the beta, which is electrons. So the important part of what he did was not only did he demonstrate that there were other subatomic particles, so there's 2 points here. He demonstrates there are other subatomic particles besides the proton, neutron, electron. Besides the proton, neutron, and electron. But he also demonstrated the existence of antiparticles, or demonstrates that particles have antiparticle pairs. That's really important here, because up till then no one actually realized the existence of antiparticles in that sense there. Okay, so that's what you see. Don't forget though, the only way he could see that was by exposing it to a really strong magnetic field. Obviously, like we talked about in module 7, when we talked about E equals mc squared, the process of annihilation occurs when matter and its antimatter counterpart interact to produce energy. Now, for an electron and positron, when they collide and annihilate each other, they do release gamma rays as the form of energy. So that's sort of like a unique thing that we can see here with the annihilation part. So let's look at the existence of other subatomic particles. We can actually quickly look into also the conservation of energy mass in nuclear transmutations as well. So let's dive in and have a look at the different evidence to that. Okay, so the first thing, just to quickly cap off last module, is that conservation of energy in fusion does exist. Okay, so spontaneous transmutation occurs, naturally for really heavy elements. The reason being is as the nucleus gets bigger, the binding energy holding it together becomes limited. Okay, so there's that. What we do know is when a particle or when a nuclei breaks itself apart, there is going to be some kind of missing energy. Okay, so that missing energy can come from the particles being released. It could come from the energy of the neutrons that are released after the so-called fusion or fission reaction. Okay, so what we're going to look at is the beta decay, And the reason we're going to talk about the beta decay is not so much about the electron itself, but rather one of the byproducts that comes from a beta decay, which is the neutrino or anti-neutrino. Okay, so when they first did observations about beta decay, you would assume that in a beta decay, all the electrons that come out from that nuclei breaking itself apart, it's going to have the same energy. So we expected this particular line in the original observations of beta decay of the electrons. What we found though was the electrons did not come out as a uniformed kinetic energy value, rather it came out as a sort of spectrum. So there was variations in the electrons' overall energy. So variations in the electrons' kinetic energy. So why was that the case? No one really knew why, because there were a couple of things that would have been violated in terms of the scientific laws, and that is firstly the law of conservation of energy. Okay, so if we had variations of kinetic energy of the beta particles, this implied that the electrons move slower than others, but how come some electrons have less energy than others? Was this energy lost? If it was lost, does it mean it just disappeared? That wouldn't work. That violates conservation of energy. It also violated the conservation of momentum. So if we had a stationary nucleus, the beta particles that got emitted from it didn't add up to zero. So what do we mean by that? I'll just do a quick little doodle. So imagine we have our nucleus here, and its momentum is zero, assuming because it's stationary. Now if I eject just a beta particle, it's got movement, so it's got kinetic energy, it's got some kind of velocity, so it has some value for momentum. So there is some kind of x value there for us. However, as you can see, if I'm just looking at the total momentum before, and I look at the total momentum after, I have a beta particle that's moving and a nucleus that's not moving at all. That's not conservation of momentum, that's not held two apart, so that can't be correct. There has to be something else that bounces this all off. So a guy named Wolfgang Pauli came up with the idea to explain what was happening here. He proposed that the variations of these energies were linked to the emission of a thing called a neutrino. So all this variations in energy, that's because some of that energy was actually given to the neutrinos instead. So variations caused by emission of neutrinos. That was his idea. And we can also demonstrate how this satisfies the law of conservation of momentum. So let's go over the same idea. We have a particle that is stationary. Okay, so momentum, let's assume stationary momentum 0. Now let's say the beta particle moves in one direction, and we say the neutrino goes in the opposite direction. Now if both directions go opposite to each other, let's say one is velocity plus, one is velocity minus, then by definition they can actually equal back to 0. So they can cancel out each other's momentum to add up to 0. Or it could be a different value depending on what the original motion was. And so we do have a conservation of momentum and conservation of energy here with the existence of this little particle. Okay, so what were the properties that were proposed by Pauli? He said that the neutrinos had energy and momentum. Okay, cool. It traveled near the speed of light. Cool. Carries variable fractions of energy during beta decay. Okay, that explains what he said. He said there was no charge, that's why it was hard to detect originally. And he said the mass was, basically massless. There was only one issue though. There was no evidence for, the existence of the neutrino. Besides the fact that we already had a problem that couldn't be solved. So we kind of had one suggestion that didn't really solve for its own existence. But the idea was correct. Okay? So firstly, the reason why neutrinos were really hard to find initially was because it had no charge and it didn't ionize. It essentially was sort of like a gamma ray in a way where it didn't really interact with anything around it. So the less interaction of the particular particle, the less likely we can actually see or detect it. Now, what you have here is a big chamber. This chamber is actually dedicated in detecting neutrinos. So we know that neutrinos really do not interact with any form of matter most of the time. So this is a big dome, I think it's in Japan, and it's actually to have the neutrinos come through and interact with a really transparent material to sort of give off some radiation, and that way we can actually detect its existence. There's a nice little TED video on that you can also watch as well. But let's actually look at the people who discovered or detected the existence of the neutrino. Okay, so it's these two gentlemen here, Cohen and Raines, I think were the names. Okay, this was in 1956, and what they did was, in using a nuclear reactor, they were able to produce neutrinos that interacted with protons. And in that process, the proton interaction released our free neutron and a free positron particle. What followed was the positron would interact with an electron and they annihilated, producing two gamma rays. So we had our positron plus our electron forming our two gamma rays, and that's energy that you can detect. You can see what's happening there. The neutron is captured by the nucleus, and in that process energy is also released. Okay, so energy is also released there. Now that's important because it actually shows the way neutrinos interact with other particles. So big tick here to demonstrate the existence of the neutrino, because it shows an interaction occurring like so. So that's actually how we discovered and detected the neutrino. Mind you though, it wasn't really the neutrino we saw in a beta decay. It's actually known as the anti-neutrino. Okay, so an anti-neutrino is the one you get for beta minus decay or the electron decay. The neutrino actually interacts with a positron emission. So that's sort of the difference you have here. When it comes to symbol writing, the anti-neutrino has this sort of little accent on top of the V, and neutrino is just sort of a italicized V there. So where do we know that the subatomic particles exist? Well, firstly, we know that in response to the missing energy in beta minus decay, we found that there is really light particle that is emitted along with the electron. The kinetic energy of this particle accounted for the missing energy that we saw in the graph earlier, and this particle is known as an anti-neutrino. The existence was confirmed when we were able to produce it in nuclear fission reactions, and so on and so on. So that is the demonstration of the particle nature, or the elementary particles besides protons, neutrons, or subatomic particles besides protons, neutrons, and electrons. Okay, so that concludes what we are going to talk about today. The main talking points is now we know that a proton and neutron are not fundamental particles. We know that the positron was one of the first discovered antimatter particles of the universe, or at least that we recognized. And we also found how the neutrino was discovered and how it was also another demonstration that it's another particle that's smaller than our atom. So hopefully you enjoyed this lesson. My name is Mr. Wong. I hope you have a nice day. If there's anything you need to rewatch, feel free to do so as well. Until next time.